Hello AP Stat students. Today we are discussing the binomial distribution. Recall that we are studying specific and special random variables in this section of the unit. We've discussed geometric distributions, which are distributions where we're looking for the first success. Today we're going to discuss binomial distributions, which are looking for any number of successes in a specific number of trials. Keep in mind that geometric and binomial distributions fall under the umbrella of random variables, which means our old formulas for the mean and standard deviation and variance still work. We can still use our calculator for those, but we will have some shortcut formulas that can get us the answer much quicker in the binomial distribution. So, binomial distributions are comprised of four things. Number one, there can only be two outcomes. We call them success P and failure Q. That is the same as it was for geometrics. Remember that Q is also considered 1 minus P, because success and failure are considered complementary events. The probability of success is constant. That was the same for geometric. So if there's a chance of an event happening is 20%, it stays 20% throughout the entire problem. Independence between trials, that just means that the probabilities do not change from one trial to the next. It's related to number two. And number four is where things go different. Because if you notice, 1, 2, and 3 are the same as they were for geometric distributions. Where this gets different is number 4. There is a fixed number of trials, n. So we are no longer looking for the first success. What we'll say is, hey, we're going to do 10 trials and wonder how many successes will we get, okay? So we could end up with 0, 1, 2, 3, all the way down to 10 successes, okay? So that's much different than geometric. If you recall from geometric, we were only looking for the first success to occur. So this is a little bit more complicated. Here's some examples of a binomial distribution. Flipping a coin 5 times, counting heads. Notice we know how many times we're going to flip it. Roll one die 6 times, counting ones. We know exactly how many times we're going to flip it. And the number of male pediatricians out of 11. That is also, we know the specific n. So that's what we mean by a fixed number of trials. We're going to know exactly how many times we're going to do whatever it is that we're doing. And we're just going to be counting how many successes we get out of those trials. That's different from the geometric, because in the geometric, we weren't given a specific number of trials. We were just waiting for that first success to occur. So here's an example. Normally, if we were in class, we'd be flipping coins and rolling dice. But so I went ahead and did a simulation for us to look at, save us a little time. So the example says, how many male children should you have in a family of 4? And obviously, you can probably guess the answer, right? It's probably going to be 2. You'd expect to have 2 boys and 2 girls if the chance of having a male and a female is equal in both 50%. Actually, in the real world, it's not 50%. There's a slightly better chance of having a girl because you need girls to keep the species going. It's a biology type thing. But for our purposes, we'll assume that that's 50-50. So we'll let x, the random variable, be the number of male children you have in a family of 4. So I flipped a coin, okay? And I basically said, if I flip a head, it'll be a male child. And if I flip a tail, it's a female child. And I just used a simulator to flip 4 coins and see how many boys I got. So these are my results. There's a graph at the right. That's a histogram of the results. You'll notice the highest peak is at 2, which is what we'd expect, right? We'd expect 2 boys and 2 girls. But notice we could get other results. We had a pretty significant number of 3 boys and 1 boy, and we even had a situation with no boys and all 4 boys, okay? And if you look at it, it's pretty close to a bell-shaped curve. We'll talk about that some more. I took those numbers and made a probability distribution, which you can see below that. So the chance I got 0 boys was 2%. The chance I got 1 boy was 24%. The chance I got 2 was 37%. 3 was 25%, and then 4 was 12%. If you add those up, they add up to 100%, of course. Then I put those in my calculator using our random variable information. I put the x values into L1 and the p of x's into L2. And then I did a one variable stats, and I got the average number of boys to be 2.21 and the standard deviation to be just a little above 1. So on average, a family of 4 should have roughly 2.21 boys, according to my simulation. Now this is an actual simulation, so remember this is empirical probability, the results of an experiment, okay? But here's where knowing this is a binomial situation helps. Binomials have shortcut formulas, okay? The mean of a binomial is simply n times p, where n is the number of trials and p is the probability of success. And for the standard deviation, we have the square root of n times p times q. N again is the trials, p is the chance of success, and q is the chance of failure. So using the formulas, the mean, my expected value, would be 0.5, the chance of getting a boy, times 4, which is my family of 4, gets me 2. So notice, very similar to our experimental results. And then for the standard deviation, I do n, 4 trials, probability of success and probability of failure is 0.5 and 0.5. And then I take the square root of that product, and I end up with 1, which is, again, very close to what I got in my experiment. I was actually closer on the standard deviation in our experimental data than I was with the mean. Okay? So the great thing about the binomial is that instead of doing all that stuff on the calculator with entering x and p of x and doing one variable stats, if I know these shortcut formulas, I can find those expected value and standard deviation very quickly. These formulas are given to you on the AP exam as well, so you'll be able to, you don't even have to memorize those. Those will be there for you. Although once you do them a few times, you'll remember. We could also find the theoretical probabilities for the situation as well. Okay, so the chance of getting no boys would be getting 4 females in a row, and that chance would be 0.5 to the 4th, which is pretty easy. I'll do it on my calculator quickly here. That's 0.0625. So that would go here. That would match up with the 4 boys probability, because again, it would be 0.5 to the 4th. Remember, these are independent events, so I can just multiply them together. That would be the same answer. So you have the same chance of getting all 4 boys as you do all 4 girls. Here's where it gets a little more complicated. If I did the 1 female and 3 male situation, which is this one, okay, here I do have to worry about where that female came in the order. So this is one option, that I would get the female first, but I could also get the female second in the group, or third in the group, or 4th in the group. As long as it has 3 males and 1 female, it fits this, X being the number of males in my family. So obviously each one of these has a 50% chance, so it's still 0.5 to the 4th for each of these. But I do have to add those then together, because it could happen either way. It could happen the first way, or the second way, or the third way, or the 4th way. Another way to do this would be take 0.5 to the 4th and then multiply it by 4. I didn't do a very good job of writing that one. It's to the 4th power. So 4 times 0.5 to the 4th, I get 0.25. So that's this try. Now, you can probably see this coming. The chance of getting 1 male would just be the reverse of this, where I would have a male first and then a female 3 times. And again, that male could be in each spot. And I think you can see where this is going. I get the same 4 options for the ways for this to happen. So this probability for 1 male is going to be exactly the same as it was for 3 males. Again, 0.25. And then if you want to, you could add up those 4 numbers that we have right now, which I'll do on my calculator quickly. That's 0.625, the 4 numbers I have already. And I can take that and subtract it from 1, and that gets me what's left over, which is 0.375. Okay, and if you wanted to go through the options, it would be, 2 males and 2 females, but there's many ways I can arrange this. I can do the 2 males first, I can do males first and third, I could do males first and last, I could do males second and last, I could do both males at the end, and the only one I haven't done is going alternating, instead of going male, female, going female, male, female, male. So there's actually 6 ways for that to happen, that I could split them, 2, 2. So I would do the 0.5 to the 4th times 6 for that one. So if I want to verify what just happened, it's still 0.375. Okay, so that would be doing the binomials with a theoretical situation. And one thing with binomials we're going to have to worry about is the order. So we're going to have to take this kind of thing into account as we do this, okay? And the chance of getting 1 female, there's many ways that can happen in this situation. There's 4 ways. It depends on when that happens in sequence. So that's something we're going to have to worry about with binomials. So we have a formula for binomials. This would give you the exact chance of getting a certain number of successes in a certain number of trials, okay? So this formula does it, where K is the number of successes. So it'd be like, I want to know what's the chance of having exactly 2 males from the previous problem. The first command is this one, NCK, and N is the number of trials, K is the number of successes. So I want 4 kids, and I want to know the chance of 2 of them being males, and we'll explain what that part is in a second. Then it's the chance of success, which is, in this case, 0.5, times how many I want, which I wanted 2 males. Then I multiply that by the chance of having, or chance of failure, which in this case is still 0.5, because having boy and girl, we said, is 50-50, times how many girls I want, which should be 4 minus 2, or 2. So the 0.5 squared and the 0.5 squared, I think that makes sense. That's really 0.5 to the 4th, right? But what is this 4C2 thing? Well, if you look down here, this stands for how many different arrangements there are of a certain number of trials and a certain number of successes. So when I do 4C2, when I do this formula, it's going to tell me how many different arrangements there are of 2 boys and 2 girls in a family of 4. Now, on the previous page, we found out that the answer was 6, but we did it by actually writing down all the options. This formula actually just gives you the answer. So this formula is pretty easy. On the top, you do n factorial, which is 4 factorial. Hopefully you're familiar with factorials. I'll review that in a second here. And then on the bottom, you do k factorial, which is how many boys I want, times n minus k factorial, which is how many girls I want. Now, 4 factorial is 4 times 3 times 2 times 1. And 2 factorial is 2 times 1. And another 2 factorial is 2 times 1. And some of these cancel, which is cool about factorials. So 4 times 3 is 12 on top, and 2 times 1 is 2, which ends up being 6. So that 6 would go here in the formula. And if you want to rewind the video, that's the formula we figured out for the 2 boys, 2 girls case when we were looking at the theoretical equation, or theoretical data, okay? So this little formula tells you how many ways or how many arrangements are there of k successes in n trials. So let's do one more example of that, that formula. Let's find the probability of exactly 3 boys in a family of 4 using the formula. So it'll be the probability that x equals 3 for 3 boys. So it'd be 4C3, that's how many arrangements there are of 3 boys, times the chance of having a boy, and I want 3 of them, times the chance of having a girl, and I want 1. And if we do that problem, we will end up getting exactly the same answer that we got before, which was 0.25. Now, this 4C3 thing, this command, this actually is built into your calculators. And what you can do is, if you look on your calculator on the left-hand side, there's a math button. You can hit that. And then in that menu across the top, you'll see there's a probability command. Arrow over to that. And then if you arrow down, you'll see this NCR command. This NCR is the same as NCK from above. And the only thing you have to do is when you're going to do one of these, you have to type the N in first. So like if we were going to simulate this one, the 4C3, we would do 4, then do the math probability NCR, where the NCR would come out, and then we would type in 3. And that on our calculator would give us how many arrangements there are. And we already know that that's 4 from the previous exercise. Okay. Now, binomial distributions can be written as follows. You'll see a capital B followed by 2 numbers in parentheses. Hopefully you remember from when we studied normal distributions that if you saw a capital N with 2 numbers, it stood for a normal distribution with that mean and that standard deviation. So this stands for a binomial distribution, where N is the number of trials and P is the probability of success. So if I wanted to describe the having 4 kids, or having a family of 4 and how many boys am I looking for, I would have said that N is 4 for the 4 kids and the chance of having a boy was 50%. So that's all you need to know. If you see that, you know it's a binomial distribution with 4 trials and the probability of success is 0.5. They don't tell you failure because you obviously know failure because it's 1 minus success. Now, calculators have some of this built in, which is really nice. If you go to the distribution command, which is the same place where we found from before normal CDF, inverse norm, and geometric P and CDF, okay? So in that same area is where you find the binomial PDF and CDF, okay? And for this, you need to know 3 numbers. N, the number of trials, P, the number of the probability of success, and then X is how many successes you want. So if I was going to do this problem we just did up here, using my calculator, I would do binomial PDF, 4 trials, the chance of a boy is 50%, and I want exactly 3. And that would give me that 0.25. So this formula does exactly the same thing as our NCK, P to the K, Q to the N minus K. That same formula, this does it for you on your calculator, okay? And all I need to know is the number of trials, the chance of success, and how many successes I want. There's another command called binomial CDF, and the C stands for cumulative, which means that the cumulative distribution, which means that we'll be looking for getting the success on or before whatever the X stands for. So if I typed in the same thing that I typed in the previous problem, the 4.5 and 3, what this function would do is figure out, all right, what's the chance of getting 3 or fewer successes, or in this case, 3 or fewer boys in a family of 4, okay? So it would take that table and it would add up those options. Now to find binomial PDF and CDF on your calculator, you have to page down that distribution area on your calculator a little ways. So if I type this into my calculator, I get 0.9375. So that is the chance of getting 3 or fewer successes. Okay, and whatever you type in here as the number on the CDF one, it includes that in your answer and goes from 3 down to 0. Now, let's do a quick example problem so you can see how this all fits together. So it says, suppose you receive a shipment of 5 monkey scooters, and nothing is funnier than a monkey on a scooter. Haha. Each scooter has a 15% chance of not working. Okay? Not working. And then it says, what is the expected value for the number of scooters that will not work? Well, this is success. Okay? Even though, a scooter not working, I wouldn't consider that a success, right? Like that's a bad thing. But remember, success and failure stand for the situation we're looking for and the one we're not looking for. So we're looking for scooters that don't work. So that is our success. So P is 15%, which means Q is 85%. So what is the expected number of number of scooters that will not work? Well, that's the mean, N times P. And they said we're buying 5 scooters. So it'll be 5 times 0.15, which is 0.75 scooters. So not quite 1 scooter on average. Okay? And remember what expected value means. Means in many, many trials, and many times we get a shipment of 5 monkey scooters, we'd average 0.75 scooters that don't work. What is the standard deviation? Remember, this is N times P times Q. Take the square root. So it'd be 5 scooters. The chance of it not working is 15. The chance of it working is 85. And you can do that on your calculators quickly. And I get 0.798, which we'd probably round to 80% if we're doing rounding to the hundredths place. What is it? Probably exactly 2 monkey scooters won't work? Well, we can do this 2 ways. We could either do 5C2. The chance of a scooter not working is 15%, and I want 2 of those. And the chance of it working is 85%, and I'd have 3 of those. I could do that. Or we could use the shortcut, which is binomial PDF. And I would do 5 times the chance of it not working times the fact that I want 2 that won't work. And either way you do this, you will get the same response, or same answer, hopefully. So 5.15 and 2. I get about 14% chance, which would be the same answer either way. For the probably exactly 4 will not work, I would do that one again the same way. Let's just do it as PDF right away. So it'll be 5.15 and 4. So I get 0.002. So very small chance that of getting 4 that won't work. What's the probability that less than 2 will not work? Now, when they do these less than 2 ones, I like to just write down what are the possibilities first. And the possibilities are that I could get anywhere from 0 to 5 not working. And less than 2 means 1 and 0. So that's the one where I want to use the binomial CDF command. And I would do 5. There's 5 trials. There are 5 scooters. The chance of not working is 15%. And I'm going to type in a 1 because I want to add up 1 and 0. And whatever I type in here, it's going to start there. And I don't want 2 because it's less than 2. Okay? So, again, I'm going to do this time binomial CDF. And I get, by rounding, 84%. So there's an 84% chance I'm going to get 1 or 0. And then my last question, what's probably that more than 1 will not work? Well, if you look at the previous picture I drew over here, the little table, more than 1 is 2, 3, 4, or 5, which happens to be the complement of 1 or 0. So I can figure out this answer pretty easily by taking 1 minus 84%, which is 16. So I use the fact that these were 84%, so this has to be 16. Because remember, all of these together, everything that could possibly happen has to add up to 100%. All right, good luck with binomial distributions. Take care.